A mass m rests on a horizontal surface. A force of magnitude F is applied to the object at the angle theta above the horizontal. The coefficient of the kinetic friction between the object and the surface is mu. Find A. The normal force exerted by the surface. B. The magnitude of the frictional force. C. The acceleration of the object. D. If F or Ft becomes large enough, the object may lose contact with the surface, which means the object will like fly or yeah. To maintain the minimal contact, what is the maximal value of Ft? So let's solve A part first. When you're solving this type of question, the first step you need to do is to draw a free body diagram. It's very important. So let's do it. These points represent the center of mass of the object. Since it's on Earth, there's definitely gravitational force that pointing straight down. This is Fg. Also, because this object is on horizontal surface, right? So there's definitely normal force that applied by the surface, and the normal force will always be perpendicular to the surface that the object is contacting with. This will be the normal force. You may ask, why Fn is smaller than Fg over here? You will figure it out after I explain it to you, but don't worry about it right now. There's an Ft that pull the object to that direction and creating an angle theta above the ground. So we should also draw the Ft on the graph. I will say this is Ft. Since the Ft is pulling the object moving that direction, and the friction is not negligible in this question over here, which means there's definitely friction force appears in this question. The friction force will be pointing that way since it is opposing the direction of the movement. So let's also draw it on the graph. One thing in this free body diagram that you should keep in mind is the magnitude of the vector of ff must be smaller than the magnitude of the fn, since fn is equal to mu. Wait, that's not right. Ff is equal to mu times fn, right? And then mu will be always smaller than 1. So ff will be always smaller than fn. This is very important. If you didn't draw it correctly in your exam, your teacher would definitely not be nice to you. Okay, let's keep on going. First, the normal force exerted on the surface. Since the object is only moving along this direction, right, or the horizontal direction, it is not moving vertically. There's no movement vertically, so which means the net force on the vertical direction is equal to 0. So right now, what you need to do is to find the components on y-axis or vertical direction. So what you need to do is to break them down. Do something like this, right? So as you can see, this is theta, right? Since it's creating an angle with a horizontal surface. So this is theta. So now you can write something like I'll write it over here, I guess. The net force on the vertical direction is equal to Fn plus Ft times sine theta minus Fg is equal to 0. So now it can explain that why on the free body diagram Fn is smaller than Fg, since Ft times sine theta is also on a vertical direction, which means this part of the vector plus Fn is equal to Fg. So Fn must be smaller than Fg in this scenario. So now we can find Fn. Fn is simply equal to Fg minus Ft times sine theta. What? Now for the B part. From the last question, we figured out Fn is equal to Fg minus Ft times sine theta, which is equal to mg minus Ft times sine theta. We know that the friction force is equal to Fn times mu. Since mu is already given you in the questions over here, which means we can directly use it, we can directly plug it to this formula. So now let's just plug Fn, the expression of Fn, to the friction force formula and find out Ff. So Ff is simply equal to mg minus Ft times sine theta times mu. Simple. Now let's do the C part. Find the acceleration of the object. The acceleration is pointing that way because of the horizontal components of Ft. However, there's also friction force that resisted from moving that direction. So we can now write the net force equation out for the horizontal component of the object. Fx is equal to, my suggestion for writing this equation is always write the big force first. For example, since it is moving that way, right? Since it is accelerating that way, which means the components here is definitely bigger than the FF. If it is smaller than or equal to, it will not be equal to as actually. If it's equal to, it will just remain constant, right? So let's write it down. It is equal to Ft times cosine theta minus the FF over here. I'll just plug in the FF you already saw from last part minus mg minus ft times sine theta times mu. And this is equal to ma. So this is what you want to solve. So we can just simply divide it, m on both sides, which we can get a is equal to a is equal to ft times cosine theta over m minus g mu plus ft times mu sine theta over m. after simplify it, I love simplify equation because it looks much better. We can get ft over m times cosine theta plus mu sine theta minus g times mu. And this is your answer for the C part. Now let's solve the D part. If f becomes large enough, the object may lose contact with the surface. To maintain minimal contact, what is the maximum value of ft? So for this question, what I would do is first analyze the words in the question. The first, the object may lose contact with the surface. So imagine if ft is like very big, it will literally just like flying, right? Lose contact. So I can say that if ft is large enough, the fn will no longer exist because when the object is like flying, is it contacting with the surface? No. So fn will be 0. To maintain a minimal contact, what is the maximum value of ft? So this is our thought process. Write an equation where there's this no fn. However, it is still like barely a contact with the ground, which means the net force vertically is still equal to 0. And then we can find ft. So let's do it. So in this also in this situation, the free body diagram will look like this. Fg. There's this no normal force. This will be Ft. That's it. Also, there's no friction force since there's no normal force, right? Normal force is equal to 0. And so Ff is also 0. So now let's separate them into components. This is angle theta. Since I can say that it still have like minimal contact, right? So I can write Fy net force Fy is still equal to 0 because it almost lost contact with the surface. However, it still hasn't. So it's like it is not moving vertically yet. It hasn't moved vertically yet. So we can write net force on the y direction is equal to 0. So now let's break them down to components. Net force y is equal to, using trig, we can get Ft times is that sine theta is equal to, no, minus mg equals 0. We can get Ft is equal to mg over sine theta. So this will be the maximum value of the Ft. If the value of Ft is bigger than this value, the object will lose contact and start flying in the sky. Or in the physical form, the object will lose contact with the surface and start moving vertically, which means the net force on the y direction will no longer equal to 0.